So, Chapter 3, scheduling. So, CPU scheduling, long-term versus short-term. So, scheduling decisions, they're made at two different levels. We have long-term scheduling that decides when a process should enter the ready state and start competing for the CPU. And then so that's the ready state. Short-term scheduling decides which of the ready processes should run next. Short-term scheduling is going to be happening often. Why? Why is short-term scheduling happening more often than long-term scheduling?
Because short term is like because it's short, they want to run it like while they're running the long term, right? So they want to prioritize that first.
Almost. Kind of. Short-term scheduling is short-term scheduling is if you're ready, basically it's going to be like time sharing. It's going to be doing that kind of scheduling, things like that. Long-term scheduling is when things are in the new state and we're trying to see which of these should we even put in the ready state. So that doesn't happen very often. That only happens when processes are created. And then short-term scheduling, that happens just any time a CPU is being shifted off because maybe it's blocked or something and put in the ready. So short-term scheduling is the algorithm that's going to be continuously running. Long-term scheduling runs every so often when a new process is created. Does that make sense? Okay, let's do this activity.
There's probably a lot of stuff that's in the ready state also.
Yes.
All the time.
All the time, yes. So it's always having to figure out, things are coming in, and so it's trying to figure out, like what to run next at any time. And that's constant. That's happening a lot. Okay, let's go to here. So here is a visual. If you want to open Zybook, you can look at that too there. So processes are created at unpredictable times and enter with new. And so the long-term scheduler is going to decide which process is moved to the ready list. This is happening less often, right? Because the completely new process is starting up. And then processes are also subject to long-term scheduling when suspended and later reactivated by the OS. That also happens. Do we remember when things are put in a suspended state? It doesn't really happen that often. That is basically like if there's some kind of error and the operating system wants to put it over here and look at it, like maybe it's worried there's a security or there's something going on. So suspended state's not happening a lot. Okay.
That's different from blocked.
That is, yes. Blocked is like when you need a resource. Suspended is different from blocked. Short-term scheduling moves processes between the ready list and the CPU. When a running process becomes blocked and later re-enters the ready list, short-term scheduling will be applied. Okay. So the only time long-term scheduling is used is when a new process, well, not the only time, I don't want to say that, but some of the few times. One is when a new process is created, and then when a process, there's something wrong. It doesn't happen a lot when it's suspended. Short-term scheduling happens like for time sharing, which is constantly happening, or when a process is blocked and comes back onto the ready list, and that's happening much more often. Okay, so long-term scheduling takes place more frequently than, less frequently than, or equally short-term scheduling.
Less.
Yes. Okay, we talked about that. Why? Because the things happening in long-term scheduling happen less than with short-term scheduling. And then a process can move to the ready list from 4 different locations. The list of new processes, the suspended list, the waiting list, and the CPU. Okay, let's kind of review what these are. There's more and more lists we're going to be talking about as we go through. List of new processes, that's just when it's created. We talked about suspended. Waiting list, remember what that is? What the waiting list is? Anybody remember? It's been a while. The waiting list is when you're waiting for a resource. So you don't have access to it yet, but you're waiting for it. And then the CPU. So a process entering the ready list from the waiting list is subject to long-term scheduling, short-term scheduling, or no scheduling. What do we think? They didn't really talk about this, so this is something we're learning here.
Is it short term?
No. No. So this is kind of details, but a block process had previously been admitted into the set of processes allowed to compete for the CPU. So the process is temporarily blocked on a resource and is moved back to the ready list immediately. It's just kind of a technicality. Okay, a process entering the ready list from the CPU is subject to what? So is it a long-term scheduling, short-term scheduling, or it doesn't have no scheduling algorithm applies to it? What do we think?
The chart helps.
You want me to go back up to the chart here? So we go from
Right
the...
there,
It's short term.
Yeah, good. Okay. Yes. So whenever a running process isn't allowed to continue running, the process is moved back to the ready list, and the decision to stop and remove the process is subject to short-term scheduling. Okay. Let's go back to the slides. Okay. So a non-preemptive scheduling algorithm is going to allow a running process to continue until the process terminates or blocks. And this is not very normal. I mean, I wouldn't say normal. This isn't common in an operating system, non-preemptive, because of time sharing. A preemptive scheduling algorithm may stop the currently running process and choose another process to run. This decision is made whenever a new process enters the ready list, a previously blocked or suspended process re-enters the ready list, or the OS periodically interrupts the currently running program to give other processes a chance to run. So these are times when we do preemptive scheduling. And so basically what happens is, even if something's running, the CPU will say, okay, is there something else I'd rather run instead of what's running right now, for whatever reason. We're going to see different reasons, or like different evaluators that it's going to use. So yeah, so let's look. So what we're going to do after this is just look at different scheduling algorithms. So again, we're just talking about scheduling processes for the CPU, some vocab, and then different algorithms you use for scheduling to decide what process to schedule next. Okay, so more activities. Let's see if I can get out of this and show. So I'm going to make this a little bigger. Hopefully it won't mess up. Okay. So it's going to, basically here we have non-preemptive scheduling. So process 1 will arrive and start executing. And then process 2 is going to arrive. And then if it's non-preemptive, P1 is going to continue while P2 waits, because there's nothing to preempt process 1. It just kind of waits. Okay. And then P2 is going to start when process 1 terminates. So even though process 2 entered at T2, like it could have been executed, it's not going to be executed till this time, till process 1 finishes. So that's non-preemptive scheduling. So under a preemptive algorithm, P1 will stop at T2. T2 was the time that process 2 was ready. And if P2 is chosen to run, P1 will wait. It might not be chosen to run. We're going to look at different scheduling. But if it is, then P1 basically stops, P2 runs, and then P1 will finish. Questions about that? So pretty straightforward. Okay, so a non-preemptive algorithm makes a scheduling decision whenever a new process arrives in the ready list. No. Basically, it's making a decision when it finishes, right? So a process changes from the block state to the ready state. Oh, a non-preemptive algorithm makes a scheduling decision whenever a process changes from the block state to the ready state. True or false?
False.
Right. So a non-preemptive decision is made only when the currently running process is finished or it blocks. Okay. A process request a non-preemptive algorithm makes a scheduling decision whenever a process requests an unavailable resource. True or false? Yes, because it's blocked. So now something else. The non-preemptive algorithm makes scheduling decisions when a process terminates.
Sure.
Okay. Now on to preemptive. So a preemptive algorithm makes a scheduling decision when a new process arrives.
True.
Yeah.
Yes, that's true. The preemptive algorithm is going to make scheduling decision when a process changes from block to ready.
Mhm.
A preemptive algorithm makes a scheduling decision when a process requests an unavailable resource. What's our consensus?
True.
Okay, good. And then, so let's read. When a request can't be satisfied, the requesting process leaves the ready list and a new process must be scheduled. So, yeah. So a preemptive algorithm makes a scheduling decision when a process terminates.
True.
So, okay. Any questions? Pretty straightforward. Mhm.
Modern OSs use the preemptive.
Yes. Yeah. Good question. The priority of a process is, okay, so we're going to talk about priority. So if we're doing preemptive, there's got to be a way that there doesn't have to be, but a lot of times if we have all these different processes, we need to choose one. We want to have different, metrics for priority. So the priority of a process or a thread is a value. It's numerical that indicates the importance of the process relative to the other processors. And then the scheduler is going to use this to decide what to run next. The priority can be constant or it can change dynamically based on some combination of parameters. And of course, we're going to talk about those in a second. The arbitration rule decides which process should proceed if two processes have the same priority. Okay, here are some common parameters used to compute the short-term priority. Arrival time. So, and we're going to look at some different algorithms that are going to use these. So you'll see these again. Arrival time, the point in time when the process enters the list, the ready list. Departure, when it leaves the ready list, either by being blocked, suspended, or terminated. Attained CPU time, the amount of time used by the process. Real time in system, the amount of actual time the process has spent in the system. So that's not only using the CPU, it's just like it's been around, using whatever. Total CPU time, the amount of CPU time the process will consume between arrival and departure. For short-term scheduling, this is sometimes called the CPU burst. External priority, a numeric priority assigned to the process. Deadline, a point in time by which the process must be completed. Period, a time interval during which a periodically repeated computation must be completed. So it's like a short deadline for different parts of the process. And then other considerations, amount of memory, things like that, current load. So these are all things that can be used for scheduling to figure out which process to use next. Okay, we are going to do this activity. We're metaphors that they like to do, which are more confusing than helpful. So, okay, for a process in the ready state, the what keeps increasing? Arrival time, attained CPU time, real time in the system, or the total CPU time?
Is it total CPU time?
Real time.
Oh, yeah, it is real time. Sorry, my brain. I was like, yes, it is. Okay. It is the real time because the real time is going to keep increasing no matter which state it's in. So the CPU time, basically both these CPU times have to do with like time they have in the CPU, different metrics. And then arrival time is just going to be one, when it came into the ready list. So it's just that's not going to change unless it's going back and forth.
What was the difference between attained and total?
Okay. Let's see. Let me make sure I don't tell you the wrong thing. Arrival and departure. Okay, this is like basically kind of predicted. We're not sure about this. This is kind of a prediction that's occurring. And this is actually the amount of time it's had so far. So this and this one you're kind of like,
Oh,
trying
you're
to figure out.
predicting how long you think it will spend.
Yes.
on the CPU.
Yes. And we're going to talk in like today about like how this you can like predict this by using past performance. So, don't do 3.18 unless you want to be confused. Okay. Okay. So we're going to go with long-term scheduling first and talk about how priority is used with that. So long-term scheduling, which decides when a process that's new should enter the ready list, uses priority. Long-term priority can be based on the same parameters as short-term priority. However, a long-term scheduler is going to basically be working much less frequently than short-term scheduling, and so decisions are made at a higher granularity of time. So basically, it's looking at like short-term scheduling, looking at like short times, and long-term is looking at larger times. That's it. And then because the arrival and departure are going to be a little different. So arrival is going to be the time of creation. Departure is going to be the time of the process destruction. And short-term arrival is basically when it came on the ready list and when it's leaving, because that's a different thing that it's scheduling. Consequently, the attained CPU time and the total CPU time have different meanings in short-term and long-term scheduling, because the long-term scheduling is like the entire overview of the process, not just when it's coming on and off the ready list. Does that make sense? Okay, and we're going to see that when we look at these scheduling algorithms, what that looks like. So let's do these. Okay, and this is going to make it very clear too. So on the top, we have short-term scheduling. On the bottom, we have long-term scheduling. So a process goes through a series of state transitions starting from new and ending in terminated. So, a process is always going to start out as new and eventually terminate, hopefully. So for short-term scheduling, each arrival is a transition into a ready state, and each departure is a transition into some kind of block state or like suspended state. Okay. For long-term scheduling, arrival is the creation of the process and departure is destruction. So that's the difference there between those two parameters. Why are we talking about these parameters again? What are we going to use these for eventually? Why are we?
Schedule.
Yes. I just want to check in here. These are used for priority, to figure out priority. So we need to understand these really well. So when we look at these algorithms that decide, we know what these terms actually mean. Okay, so in short-term scheduling, the arrival and departure means like the last time you came onto the ready list and the last time you left the ready list. So it's a short, and you can have several of them. It's going to be changing. With long-term scheduling, you're just going to have, basically, it's not going to change. It's like you came and then you left. That one kind of thing. Okay. The attained CPU time accumulates between arrival and departure while the process is running. That's what that means. For short-term scheduling, the attained CPU time restarts with each arrival and keeps accumulating until the current time. So it's just changing continuously as it's coming back and forth off the list. For long-term scheduling, the attained CPU time keeps accumulating, so you're just adding it. So short-term scheduling, it's resetting. Long-term scheduling, it's basically accumulating that value. The real time for short-term scheduling start with each arrival and accumulates until the current time, regardless of the process state. The real time for long-term scheduling starts with the process creation and accumulates until the current time, regardless of the process state. Okay. The total CPU time is the accumulation of all CPU times from arrival to departure. For short-term scheduling, the accumulation restarts. And long-term scheduling has only a single arrival, thus the total CPU time is the accumulation of all CPU times from process arrival. So the moral of that story is short-term is kind of resetting itself, and long-term is like accumulating for these values. Okay. And then we just have some activities, so let's do these. Arrival departure times correspond to process creation destruction in what scheduling? Short, long term? Yes. No, it's long term. Sorry, did you say short term? I'm just sorry. Long term. So under long term scheduling, a process has a single arrival and single departure. In short term, it's basically when it came on the ready list, when it left, and that happens over and over, right? Because it's going on and off the ready list as it's being blocked and suspended, different things happening. Okay. So a process P starts running at time 0, becomes blocked at time 2, and starts running again at time 5. P's attained CPU time under short-term scheduling at time 6 will be how many units? Okay. Yeah, now I need to turn my brain on too. Okay. I know, I feel like we do need a diagram here. They won't be able to see this, but we'll be talking through it. So, okay, what's happening here? Okay. P starts at time 0. Here we go. And becomes blocked at time 2. So we're going to say 0 to 2. I shouldn't draw that there. And starts running again at time 5. So 2, 3, 4, 5. Okay, so this is like basically when it has the CPU, and this is when it doesn't. Okay. So at time 6, what is the attained CPU time? So let's make that shorter. So it's basically how much time you've had. This is with short-term scheduling, though. Remember, short-term scheduling resets itself. So basically, when we're here, it's just 1. Does that make sense? Okay. Yes. Okay. P's attained CPU time under long-term scheduling at time 6 would be what?
3.
Yes. Not 2, 3. Good. Okay. If P terminates at time 7, the total CPU time under long-term scheduling will be whatever time. How many time units?
5.
4 to 2, and then 5 to 7.
Yeah.
So what are we going with?
4.
Yes. The total CPU time under long-term scheduling accumulates from process creation until process destruction. Make sense? Okay. So this is basically just like basics of scheduling, like vocab. Now we're going to start looking at some of the algorithms that are used. What time do we have? Oh, we're good. Okay. Okay. So a batch process performs a long-running and generally repetitive task that doesn't require any intervention from the user. So this will be something like payroll or scientific calculations or apparently insurance claims processing. Something you just kind of like start and then you can leave, right? So now we're going to basically talk about different scheduling algorithms. And you know what? I want to go back to this really quick. Okay, so we're talking about these because time sharing really isn't happening with these, so that's why it's scheduling of batch processes. These are processes that you're just going to run for long periods of time, but we're going to see they can be preemptive. So we're going to talk about not preemptive, and then we'll go on to preemptive. Okay, so first in, first out. It's also known as first come, first served schedules processes strictly according to a process arrival. So this is the simplest algorithm you can go with. The earlier the arrival, the higher the priority. So that's what the priority is. It's like arrival time. So because of the way it works, first in, first out is
Like
not
a stack,
preemptive.
right?
Yeah, it is like a stack, yeah. Okay, so let's do these here. Oh, ask, okay. Okay, so here we have 3 processes. Oh, maybe I, okay. They need to be scheduled. Process 1 is going to arrive at time 0. It's going to need 6 units of CPU time. Uh-oh, my bad, okay. P2 arrives at time equals 1 and needs 3 units, and P3 arrives at T3 and needs 2 units. So we have this nice graph. P1 arrived first, so it starts, because this is first in, first out. P2 arrived second, but it cannot start until, because we're doing non-preemptive, so it cannot start until P1 terminates. And then P3 was the last to arrive, and so it's scheduled last, and it will start after P2 terminates, when TT is 9. Okay, so let me plug this in. We're going to draw a picture here and figure out when these... Actually, I don't know if we need to draw a picture for this. It's pretty simple. So start of process 1. When would process 1 start? It's pretty straightforward.
0.
Time 0, yes. Good. Okay. Then when will P2 start? It's a little bit of a trick question. Probably shouldn't tell you that. Yes, because P3 actually got there first, right? So I will put that in. Okay, good. Okay, so 8. Oh, okay, I think we just... Okay, so 0 is going to go to 5, then... So 5. I think. Oh,
Yeah.
7. What am I missing?
It starts at 0. I say 1.
Oh, yeah, yeah. And then it starts at 5 and goes to 2. No, wait.
Well, only 9 because it goes
It
to
starts
5
at
and
0.
3 and 1. So
It's gonna go through P1 first till it gets to 5, and then it's gonna go through P3 for 2. So
Oh, because I'm
Oh.
yeah, yeah. Oh, got it. Yeah, sorry. Okay, so it's going to be,
I think
what did
it's
we say?
7.
No, it's going to be 9 because it comes in earlier and then it has to wait 5 and then it runs.
Oh, yeah.
Oh, but we're saying when it starts. So the start should be 5. That's
the
what I
start.
put.
That's when P3 starts.
What were you doing? Isn't that what we want?
P2.
Oh! Okay, when P2 starts, you're right. So it's going to be 5 and then 9?
Yeah.
Yeah, okay. Sorry. Yes, okay. And then start of P3.
5.
Yes. Okay. Does that make sense? So they just switched it up on you there a little bit. Okay. The shortest job first algorithm is also called the shortest job next. Schedules processes according to the total CPU time requirements. So the shorter the required CPU time, the higher the priority. If multiple processes have the same CPU time requirement, then the arbitration rule can select a process. So shortest job first. So let's just look at this really quick. Okay, so 3 processes need to be scheduled. Process 1 arrives at T0, needs 6 units. Process 2 arrives at T1, needs 3 units. P3 arrives at T3, needs 2 units. Okay, process 1 arrives first and starts immediately because we only start scheduling when something's on the ready list. Nothing's on the ready list, so it just starts. Okay, P3, and it basically, this is non-preemptive also, so you have to wait till it finishes. Did it make that very clear? Yes, I didn't say that. Shortest job first is non-preemptive, so that's important. Okay, so P3 has a shorter total CPU time requirement. Okay, so basically when we have 2 things to choose between, we're going to choose the one that has the shorter total CPU time. And so it's going to start as soon as P1 terminates, and then P2 starts when P3 terminates, and that's it. So that's how the decisions are being made.
Can you go back to step 1?
Yes.
Because aren't they saying, like, we know about P1 and then P2 comes on to the scene first?
It does, but we're doing shortest job first. So what happens is while this one's running, these two are both on the ready list. So
At the same time?
at the same time. Because like in first in, first out, it's just whoever gets there first. But with this one, it's like they're both kind of waiting, and so it chooses the one that runs the shortest time, basically.
Okay. Because, I don't know, just the way they shift it over, it makes it look like
Yeah.
we have P1, so we run it, and then P2 comes onto the scene. That would be the shortest one. So,
Oh, okay, that's a different one. Yeah, I see what you're saying. No, it's not run because it's non-preemptive. It's blocked, so it's not running.
like
What
I
do you
would
mean?
move P2 and P3 together at 1, like at the same starting time.
Oh, I see what you're saying.
If you want to compare both of them at the same time.
Oh, but okay. So I think what they're trying to show you is these both arrive at different times but this one still's going to go first because it's shorter. So they're showing you the difference between this one and first in, first out.
Oh, because P1 will just run.
Yeah.
So P2 does come onto the scene first, but P3 comes onto the scene while P1 is still running.
Exactly.
So then you're comparing both of them.
Exactly.
Okay.
Yes. Yep. If it happened differently than that, like if P2 was running and this one came on later, even though it's shorter, it doesn't know about it, so it would get run next. Does that make sense?
Yeah, like if P2 was shifted over to like 7,
Yeah.
then you would run P2 or you'd run P3 first, and then you'd run P2.
Yes. That would also happen. Yes.
Okay.
It's the scheduling is just happening when you have to choose between two things. If you don't have to choose between two things, it's basically whatever's there, which is first in, first out. Yeah. Okay, good question. Okay, so let's do this activity. So let's draw a. Okay, so we've got P1, and it's going to arrive at time 0, and it is going to go to 5. Okay, and then P2 is going to arrive at 3, and then go 1. And then P3 is going to arrive at 2 and go to 4. So so we stick a 6 here. Okay. So when will P1 start?
0.
Yeah. Because it's the only one there, and so we just start 0. Okay. So what's going to start after P1 finishes?
P2.
P2, yeah, because it's the shortest. So it's going to start at what time? What time? What do you think? Yes. Oh, did you say 5? I didn't
No.
hear you. Oh, okay. And then when will P3 start? So P2's running, so we went 5, and then that's 1, so 6. Is this making sense? Okay.
So this one is like whatever is the previous is and added together. Like for example, if there's 2, because there's 5, it's 5 because it's on top.
No. So what we're doing here is the idea is if there's one process, that's in the ready list, you go with that. But if there's 2, you choose the process that's got the shorter time that it'll take to run. So it's the shortest job. So the idea is we want to put the shorter jobs first and just get them over with. How are we doing on time? Okay. Let's just do, okay. Shortest remaining time. So the shortest remaining time algorithm schedules processes according to the remaining time they have needed to complete the work. So it's basically not how long they are in general, but how long they have left. Okay. The shorter the remaining CPU time, the higher the priority. If multiple processes have the same remaining time requirement, then the arbitration rule can select a process. So the shortest remaining time is the preemptive version of the shortest job. How do they skip this one. Why did they do that? That's annoying because we said shortest job first and they're calling it the alternate name. Shortest job next, which is the same thing. So it's the preemptive version of this. Okay, shortest job first. So now we're getting into preemptive algorithms. Okay. So let's go. So earlier, the two algorithms we talked about, first in, first out, shortest job first, both like non-preemptive. Now we're getting into preemptive. Here we go. 3 processes need to be scheduled. P1 arrives at time 0 and needs 6 units. P2 arrives at time 1 and needs 3 units. P3 arrives at T3 and needs 2 units. So we've got this. P1 arrives first, so whatever gets there first, there's nothing else, so it just starts it. Okay. Then P2 comes in. P2's remaining time is 3 units, while P1's remaining time is 5 units. So P2 is going to preempt process 1. Okay, so what's happening here is when process 2 starts, the scheduler says, should I keep running process 1 or let process 2 have the time? It looks and says, well, okay, process 1 has 5 left. And then process 2, now this is what I'm not, has 3 units right here. So it's 1, 2, 3. So let's take process 2 because you know, it's got less time remaining. It hasn't even started yet. So it takes process 2 and starts. And process 1 gets put on the ready list. Process 3 arrives at time 3. Process 3 remaining time is 2 units, while process 2's remaining time is 1 unit. So process 2 continues running until the time is 4, because it's going to finish. At t equals 4, process 1 remaining time is 5 units, and process 3's remaining time is 2. So P3 starts and runs. And then process 1 finishes. It's the only thing left on the ready list. It's taken off. Finished. Questions about that? Okay. So the remaining, did I say to do this one? Let's look. We skipped one of these. Yeah, we're skipping that one. It's confusing. Okay. Let's do, we did 3, 5, 3, 7. So we're going to skip that. You're not responsible for that. Okay. Let's draw this out. And after we do this, we will take a break. Okay. So.
Which algorithm is this?
This is the shortest remaining time, the one we just went over.
Okay.
What did I do with the, there it is. Okay. Okay, is that the same one we did? Did I just erase the same one we did?
Yeah.
Oh, that's nice, but I'll just start over. Okay, 0 through 5. I'll just draw it again. Okay. Then we've got.
Arrival time at 3. And
You know-
it's 1.
But actually, this graph's not going to be exactly the same, so let's wait. Okay, so we're starting process 1, it's running,
Yes.
right? And then at time 2, process 3 is going to arrive. So at that point, how much remaining time? So we're at 2.
Can you draw a little higher? Because that
Oh,
monitor.
you can't see?
I can't see the monitor right in the way.
Oh, yes, I can. Okay, process 1. Okay, so process 1 is running till time equals 2. That's when process 3 arrives, right?
Yes.
So what's the remaining time on process 1?
3.
3. And then what's the remaining time on process 3?
4.
4. So process 1's going to continue.
Yes.
Okay, until
Until 2.
until 2 comes in at time 3. So let's go out here to 3. And then what's the remaining time on
2.
process 1? And then process 3 is what? I mean,
2 is
process
1.
2 is
2
1.
is
So we're going to
1.
run process 2. Okay. So process 2 is going to run to 4. And then let's see. We're back to process 1. Its remaining time is still 2, right?
Well,
So we'll-
1. After
No, process 1 is 2 still.
Yeah,
Because
and
we
then
stopped it.
process
Stop.
3 has 4.
Yeah.
So now we're going to finish running process 1, and it's got 2. So that's going to be 4,
So
5.
6.
No, 4. Yeah, 6 done. Okay. And it's done. And then process 3 will start at 6 and go to 4. Sorry,
So
we're running out
10.
of space. We're gonna
Start
to
at
10.
6 and
This is process 3. Okay, so let's answer the questions. Okay, CPU.
10. Start P1 is 3. Oh,
I mean-
0, 0.
Yes. Okay. Process 1. When does process 1 end?
3.
3 and 6.
It doesn't really. I guess it means it's
Done.
done. Yeah. So, yeah. When does process 2 start?
3.
3.
4.
And then ends. And then process 3. Okay.
Oh, so good.
We're awesome. Okay, so this is a good place to stop because this is actually, we're done with those algorithms, the scheduling algorithms. So we're going to start something new. So I will just grab some water and then we'll just keep going. Okay. Do you guys have any questions about the programming assignment?
I
general?
Started, but is it on Wednesday? Still on Wednesday.
It's due tomorrow. End of day.
I still feel like I just created some objects and just
Okay.
set like this thing's this and this thing's that and print that.
Yeah, it's pretty easy. It's just the first one.
We're
It's
gonna-
nothing like groundbreaking.
Are we like gonna build on this project?
Yeah, we're gonna
Kinda
like
simulate an
yeah.
operating system?
not so. I don't think we have enough time for that, but we're gonna build on it, put things in it as we learn about them. Yeah, so it's not gonna just be like yeah, we're gonna start like we can do scheduling with these processes because we can like we'll have the time allotted, and then you can look and see, and so we can use them for things. It won't be an entire operating system though.
I made some methods to like you can tell a process to stop
Mhm. Cool.
and it will just kill all the children and
That's awesome. Yeah.
kill
Yeah.
itself and
And kinda, like,
the youngest and oldest siblings it's got together
That's cool. That's
just to
very
do
nice.
something.
Good. Yeah, I made it pretty easy at the beginning, but yeah, we're gonna be like adding to it, and then it'll be used for sure. Okay. Where's my? I'm just going to, for these people at home, I'm gonna put in breaks. I don't have to like. So I don't have to like fix this. How can I? There. They can just watch that until. Because I keep having to like paste things together. It's a pain. I'm not a star. I can't do that anymore. It takes time. FFmpeg is my friend, but still, it takes time. Okay, I'll be right back.
Is that not like super easy? Well, yeah, the instructions are just like make an object that has these properties. There's like 4 of them you make, and then you just in the main you're like create this PCB with this ID and set its priority to this. And
So you can really like turn lights on drugs, right?
yeah, I can show you if you want to see.
Do you do geology?
Yeah. Yeah, so there's like this class, and then she says like it's got an ID, it's got a state, which is an array of integers, and then there's these 4 objects that you make. Like memory. It's just got an address, and she said just make it a random number. And then resource just has an ID and a resource type. Schedule is literally just an integer. But this one you needed to track. You want to be able to get like how long the time has elapsed since it was created. And then just in the constructor, I just set it all to the default she wanted. And then like in your main, you're just like creating a process, printing that process, set its state to running, just like that.
I have shirts if you want them.
You have shirts.
Yeah, because I'm the advisor for WIT, and we have all these old shirts, and I just like offer them periodically. Like, please take them. CMU Computer Science. It's a polo.
Cool.
It is extra large. We also have a red one that's extra large. You don't have to take them, by the way. I just don't want to throw them in the trash. They're nice. Large. I already have one. Anybody want one?
I'll take the red
I'll
one.
take one too.
Large. Okay, what size do you want? We have 2 larges.
I think I'll take large.
You want to take the large?
Budget's gonna be.
There you go.
I'll take this small.
I don't have the small. I'm sorry.
It's gonna be so big.
Want the XLT?
Do you want the red one?
Yeah.
Okay.
I'll take the other extra.
Okay, cool. Yay.
Sweet.
Awesome. Getting rid of mine.
I feel left out here.
I'm sorry.
Just kidding.
I mean, I have the large. You could shrink
just didn't
it.
want
Put it in the hot water.
I'm good.
You just like do it and dry it too.
Yeah, dry it and wash it. Okay. Take this back and we'll get through.
Did you guys watch Game of Thrones?
I did.
What did you guys think? What was that?
Game of Thrones. Watch it.
I never watched it. I'm not gonna season 1.
I don't think there's a lot of things that haven't finished.
Unfinished.
I mean, like there's a lot of things that like the next animals.
Yeah.
I don't know. They might make another season.
No, they're
I'm not quite watching like the season 1, but like 5 episodes. I'm sure I'm into it. I don't know why.
What
Yeah.
now? Oh. Did you guys have a question for me? Oh.
We're just talking about Game of Thrones.
Oh yeah. I haven't. I read the recap. I didn't watch it. Yeah.
Oh, shit.
Don't spoil it.
I'm not gonna spoil it. You guys didn't watch it yet?
I mean,
I did.
Outfits. I don't know.
I mean, I don't really. I don't know. Is it like heresy to say I don't really like that show that much?
It's okay.
My husband watches it, and I watch it kind of like passively, like as I'm walking around, so I kind of know what's going on. So I'm waiting for him to get back to like finish watching it, but I just couldn't wait because everyone's talking about it, so I just read the recap. So I don't know. I'm like, okay.
Seasons 1 through 5, and then
Yeah.
it just got worse and worse.
Yeah, I've heard a lot of people were disappointed in this last season. Maybe they just got tired. I don't know. I don't know. Did the writers change? Is
They
the same
ran out of
writers?
books.
They ran out of actual. They did. Is that really what happened?
Yeah,
Oh,
they had to start just going on the outline.
and then he wasn't helping them. Like, what's it?
But he just gave him like the outline.
Oh, so not like really
it's not
part
like
of the
They
writing.
had the actual dialogue, but
Right. But how much money is there into Game of Thrones? It seems like they could have figured that out, you know.
They're making so much money.
Isn't it like the most expensive show or something?
Yeah.
I don't know. Okay. I'm watching Big Bang Theory right now.
That's still going.
It just stopped. I'm like watching the last season. It's pretty. I mean, that's a completely different kind of show. It's not.
Anybody die?
Yeah, I mean, it's not the same kind of show. Anything else good on? I'm out of shows. Into show?
Do you have Hulu?
Yes, I do. I have all the streaming things.
Have you watched Good Doctor?
Doctor Who.
Good Doctor.
Good Doctor. Good Doctor. What's that about?
That's in Hulu. It's like this guy like.
Oh yeah. Who's got? Yes, I did watch that. That's good.
Yeah.
Yeah, I've watched that. I'm all caught up on that.
Seen the new season?
There's a new season of Good Doctor.
There's a new season.
It just. I don't think so.
I don't think so.
Okay, let's go to.
I started watching Community. on Hulu.
That's a good show, but I stopped watching it after a couple seasons. But I think it still was good.
Yeah.
Yeah, it's got really good writing.
And then Dirk Gently's Holistic Detective Agency.
I started watching that too, and also got bored. I think, but it's good. It is good. Like, it's really interesting. It's a really interesting premise. You know what I mean? It's like you don't see anything else like that.
Yeah.
That's cool. Yeah, I should probably restart watching that.
At least just the first season. It's really tight.
Yeah, I should. I think I need to start. Maybe I'll finish that. That would be. There's so much good TV. That's why I think I get bored because I'm like, this show's better. They're all good, but it's like this show's a better show, and then I go off and then I go back. You know, because there's so much good stuff. Okay, let's go. We're talking about, you know, like this CPU, like this process is going to run this many units. We don't really know how long a process is going to run, right? Like it can't tell. Like when you're opening Word, you can't. You know, you're not telling. You know, the CPU, I'm going to run this for 1 hour, or, you know, anything like that. So it's actually estimating the time. It's estimating the time based on a couple of statistics that it kind of keeps track of. So for long-term scheduling, the total CPU time is measured between the process creation and destruction. So we've talked about that. So the time can be estimated from previous runs of the same program or may be supplied by the programmer. Usually it's estimated. I'm not really aware of, I've never told the CPU I'm going to be running this program this long. I'm assuming maybe in like some sort of, you know, programming that I don't do that they do that, but I'm not sure how, you know, how often that's done. So for short-term scheduling, the total CPU time, which is often called a CPU burst, changes for each arrival departure period. So the total CPU time is not known in advance, but can be estimated based on past behavior. So the most common approach is going to use what's called exponential averaging, which combines the last estimate of the total CPU time with the last actually observed total CPU time. So the estimate is going to be S, and the observed is going to be T to predict the next total CPU time. So it's like a balance. Okay, so, and that's just what I talked about. Here is our, our equation. We've got Tn, which is the observed, and then we have Sn, which was the predicted, and they have this alpha, and alpha is where we have a little control. So alpha controls the relative weight of the last observation versus the history of past predictions. Okay, and so we have a nice infographic here. So in this case, we have alpha is 0.8 in this one, and in this one we have alpha, in this graph we have alpha 0.2. So if alpha is large, each prediction is based mostly on the last observed value. So that's what we're actually, you know, what's happening in the system. The advantage is that the predictions adapt quickly to any changes. So if, like, you know, what's happening in the operating system, your next prediction is going to be like on target. I mean, it adapts quickly. The disadvantage is that the predictions also follow any outliers resulting in erratic behavior. So this spike here at time 8 is followed by a spike in predicted behavior. So sometimes, you know, things are going to happen, and you're just going to have these like kind of outlier things happen, and then we're going to actually, our prediction will follow that, even though this is something that's random kind of. It doesn't usually happen. So we don't really want to follow this peak with our prediction, but we do, because we're giving what's happening in the system, the alpha is going to be bigger for that. Okay, with a small value of alpha in here, each prediction is based mostly on the weighted history of past predictions. The advantage is predictions ignore outliers. So see, here we have this like random spike for whatever reason, and it's kind of ignoring it. It does ignore it, but adapts more slowly to changes. So this spike is ignored, mostly a little bit here, but mostly ignored. And the disadvantage is that the prediction curve rises slowly here to catch up with the observed values. Okay, so these are two different alphas, and we can kind of see what's going on there. And this is basically to predict the time of CPU, okay, for a process. So the main objective in scheduling batch, wait, sorry, I feel like there was an activity, but I think it's later. Okay. The main objective in scheduling batch processes is to maximize the number of processes completed per unit of time. The order in which processes are executed cannot reduce the total CPU time of the individual processes, but can reduce the waiting times. So we're basically moving on from that out to a different thing. Okay. The turnaround time of a process is the time between its arrival and departure, and is the sum of the total CPU time and the waiting time. The average turnaround time for a set of processes is the mean of those individual turnaround times. And so this is something, like we're using scheduling algorithms, we want to basically minimize average turnaround time. Another important objective is to guarantee fairness. Starvation is the indefinite postponement of a process while other processes are allowed to proceed. This can happen. Both shortest job first and shortest remaining time can lead to starvation. We're about to see that. Okay. So basically, this average turnaround time, we can use that with these different scheduling algorithms and compare them using the average turnaround time and if starvation occurs. And so there's like pros and cons based on those two measures. And that's where the activities come in. Okay. And I forgot to add this in, and so I will put that in the slides, but let's do these two. So determine the predicted value Sn plus 1 for Sn equals 10 and Tn equals 12. So let me just write the, it's very simple. Let me write this equation up here. Okay, so Sn plus 1 equals alpha Tn plus 1 minus alpha Sn. Okay, that's our equation. So if Sn is equal to 10 and Tn is equal to 12 and alpha is equal to 0.5, so that's going to be 0.5. What is our estimated predicted value? And this is our predicted value for the time that a process is going to take to run. So this is going to be the time that we saw last time it ran. This is what we predicted last time it ran, what we thought it would run. How it would run. So what is this? We got 6 plus, yes. So we're going to get 11. Good. Okay. And then if alpha is 0.1, so that's going to be, so, is that correct? Because that seems like, I mean, 0.1 of 1.2 is going to be 12 is 1.2. I just didn't remember that we had a floating point number. So anyway, okay. And then that's going to be 9.
2.1.
So that's going to be
Oh, that's 9.
our 10.2.
So that's 1.9.
I just didn't remember there was floating point.
10.2.
Yeah, okay. Okay. What should be the value of alpha so each prediction is based solely on the last observation? So let's look at our equation here. So the last observation is Tn. So if we don't want Sn to count, what should alpha be? And we don't want Sn to count, we want Tn to be the only thing that we're using.
1.
Yes. Yep. And then what should be, do we see why that's the true? Because then that'll be 1 and that'll be 0. So Sn's completely gone. And then what should be the value of alpha so that each prediction is based equally on the last observation and the last prediction? Somebody else answer. Equally. What number do we choose so they're balanced? So alpha's the same for both of these. We want alpha to be the same. How do we, what's 1 divided by 2?
2.5.
Yeah. Yep. Okay, so 0.5. Oh, come on. Come on, computer system. They could do better than that. Okay. There we go. Does that make sense? I know what's going on. Okay. So, now that we have this, okay, so we had talked about that. Then we talked about using the average turnaround time and starvation to compare scheduling algorithms. So we can kind of see which is better in what circumstances. So, let's kind of look at this and I'll explain it as we go. Okay, so P1 arrives at time 0 and needs 6 units. P2 arrives at time 1, needs 3. P3 arrives at times 3 and needs 2. Okay, so this is what's happening. So this is how first in and first out works, right? If we schedule these, this is what it looks like in this order. And so what they're going to do is figure out the turnaround time. So it's basically when you arrived and when you ended. So process 1 got there at 0 and ended at 6. Process 2 got there at 1. Wait, I understood this last night. Yeah. 1 and then it stopped at 9. I look at this a little, I see what they're doing. Okay, basically it's the time that they were on the CPU.
Oh,
so you can just copy, so it's like 5, this one got in at time 1, it arrived, not the time in the CPU, the time it arrived, and then the time it left. So it got there at time 1 and it actually terminated at time 9. So that's 8, right? 9 minus 1 is 8. They split it up between waiting and CPU, so that's just a different way to look at it. So you can do like the time that you requested, you know, that you arrived on the ready list. So to me, how I like to look at it is basically when you get on the ready, when the process is on the ready list versus when it actually, you know, finished running. So that would be 8. And then this one waited 6. It got into the ready list at time 3 and actually finished at 11. So that would be 8. And so if we add 6 plus 8 together, that is going to be 22, and we divide that by 3, and that's our average turnaround time. So this is the average turnaround time for these processes, like that, you know, arrive at this time, using first in, first out. Does that make sense? Okay. Now, in shortest job first, P1 starts because no other processes arrive. P3 shorter, and then it runs before P2. And we've talked about this algorithm, so I'm not going to go through it again. What we care about is the turnaround time. And so P1 gets the, remember this is, these both are non-preemptive, so you have to wait. So P1 goes from 0 to 6, and then P2 arrives at time 1, so it could have ran, but it can't. And then it actually completes at 11, so that's 10. So that's just how I do it. Otherwise, you could say it waited for 7 and ran for 3. And then this process gets there at time, what is it, 3, and then actually finishes running at 8, so that's 5. Or you could say it waited for 3 and then ran for 2. Anyways, when you divide these, when you add these together, it's 21, and then divide by 3, that's 7. So here, shortest job first has a shorter turnaround time than first in, first out. Okay. And so it says, the arrival of new processes of length less than 3 prior to time 8 could lead, this is a thing that's bad, lead to an indefinite postponement of process 2. That's called starvation. So that is something, though, that could happen with this sort of algorithm with the shortest job first. You can have starvation happen where a process never gets run. Okay. Under shortest remaining time, P1 is interrupted by P2, and both P2 and P3 complete before process 1 resumes. So here we have process 1. It basically got there at 0 and doesn't finish to 11, or either you could say it had 5 waiting time and 6 running time. Either way. Process 2 is going to basically get there at time 1, end at time 4. 0 waiting time, 3 time running. And then process 3 is going to basically get there at time, it's hard to tell, 4 and finish at 6. All right. No. Okay. What am I missing here? I think that's wrong.
Isn't P2 wrong also? Well,
No, that's correct, because that's
it's
the
not
waiting time.
So wouldn't P3 have no waiting time?
I think it should be 0 plus 2. I think that's an error.
Or 0 plus 3?
I think it only runs for 2, right?
It's hard to tell.
I know.
Yeah, really. But yeah, 0 plus 2.
Yeah, that's wrong. I'll have to make a note for them. I'm going to say for, what is it? SRT P3 should also have 0 waiting time, I think, unless I'm missing something. Okay. And so its actual turnaround, average turnaround time is 17 divided by 3. If we took that 0 off, it would be 16 divided by 3. But anyway, it's less than the other two. The arrival of new processes of length less than 5 prior to time 6 could lead to an indefinite postponement of P1. So that's another, also you can have starvation with shortest remaining time. And so that's just basically comparing the 3. Okay, so let's do these activities really quick. Let me draw here. Okay. The average, okay, so we have process 1 arrives at time 0. And needs 100 CPU units. So we're going to say 100. We don't know. Okay. And then process 2 arrives at time 1. So we'll just do that. 0, 100. So we wrote that up here. Okay. The average turnaround time under first in, first out will be what? Okay. So that's going to be, for first in, first out, we're going to basically have a process that runs from 0 to 100, and then from 100 to 101. So the turnaround time for this is going to be 100, plus, what's the turnaround time for this process? 101. It's the time you enter, the time, no, 1. So it's going to be 1 to 100. So that's going to actually be 99. No, wait, it's going to be 100. My brain. I
Which
need some more
process?
caffeine. Okay, process 2 gets in at time 1, but it has to wait till time 100, and then it runs to 101. So it's when you got on the ready list minus 101. So it'll be 101 minus 1, so that's 100. Okay. Divided by 2 equals what? 100. Let's check it. Hopefully I'm right. Yay! Okay. Does that make sense why that happens? Okay. Let's do shortest job first for these two. So that is also non-preemptive. So it's going to be exactly the same. Okay? Right? Yes. Let me make sure. If it's non-preemptive, it should be... Let's go to shortest job first. Yep. So it will be the same. Yes.
Why will it be the same?
It will be the same because this one starts at 0 and runs 100 units. Even though this one comes in at 1, it's not going to preempt this. It just has to wait. Even though it's a shorter job.
Uh-huh.
So, yeah, you know. Now, if at the same time this one came in and this was like 2, this is the starting time. This one, I mean, let's make it shorter. Let's make this 2 and this one 1. Let's say that's the case. Then between these, this would run and then that one.
Mhm.
But still, this one is going to have to wait. Both of these are going to have to wait till this to finish. Okay. Okay. The average turnaround time under shortest remaining time will be how many units? So this one is preemptive. So process 1 is going to start, and then at time 1, this one is going to appear. So this one will have what, how much time left when process 2 gets into the mix, gets in there.
99.
I'll have 99, right. So then process 1 is going to run. So this goes from 0 to 1. And then process 1 is going to run from 1 to 2. And then process 1 is going to run from 2 to what, 101?
Yeah.
Okay. And so the turnaround time for this one is going to be 101, right?
Yeah.
And then this one is going to be 1 because it ran immediately. So that's going to be 102 divided by 2 equals 51. Okay. Does that make sense? We did there? So the turnaround time is basically when you got on the ready list to when you actually finished. So like that's 1. And then this one is like it got here at 0 and it finally left at 101. And then we just add them together and divide them by however many processes. So there's 2. So let's put that in, double check. Okay. I want to do this. CPU time requirement. Yeah, this will make us think about it. Okay. So, if processes have exactly the same total CPU time, then first in, first out, and shortest job first yields the same average turnaround time. If they have the same CPU time. That's not talking about when they arrive. I don't think so. So let's say they both have 3. If one's there and then the other shows up, that has the same turnaround time. Shortest job first. I don't think so. Unless I don't know. Maybe I'm overthinking it. Well, shortest job first. If that are, oh no, wait, but it's blocking. It's blocking. Yeah, I think it is the same because they're. Let's just see.
First in, first out. The turnaround time would be 3, right?
Yes.
The average.
And then also for shortest job first, because even if this one comes in the middle, it's got to
gonna
wait.
keep running that, yeah.
So I think it's true. Yes. Okay. Shortest job first and shortest remaining time also yield the same. I don't think so. Do they? Okay. Let's see. So if this one comes in, well, maybe. Okay. Let's say this one starts and this one comes in at time 1. I mean, okay, here's 0, and then this one comes in at time 1. This one's going to have 2 left.
So
it's going to, this one will also have 3, so it's going to continue. So I think it's the same from that example.
if it's shortest job first, it's not going to change.
No.
They're both the same.
Yeah.
If it's shortest remaining time, it'll keep running the first one.
It'll keep running the first one anyway.
But the second one will have a longer wait time because it
Mm.
could.
Oh, I see what you're saying. It will have a longer, but doesn't it have the same wait time? Even when it's.
Yeah.
Okay. Shortest job first and shortest remaining time could lead to starvation. I know 2 of them. Right? We're going to cheat on that one because I can't remember which one does starvation.
Starvation is just like, is that where you have like a really long process, but you just keep getting short ones?
Yeah,
in,
basically,
so
yeah.
it just never runs it.
Yeah. Okay, so here we have shortest job first, shortest. They can lead to starvation. Would they at this point? If they're both the same, would they lead to starvation? I feel like no.
Is that what it's asking?
Yeah, if they have the same length, then you won't get starvation. Because, yeah, that occurs when you have like a really long process and shorter ones, but they're the same length. Okay. Okay, we are now going to do this exercise. What time is it? We have like 17 minutes. Okay, there are 4 of you. You guys are going to do this. So go into groups of 2, and somebody do 3.2.1, and somebody in one group do 3.2.2. And then we're going to talk about it. Just get as far as you can. We are going to have we have 16 minutes, so we'll say 10 minutes, and then we'll talk about the answer. So yeah. And we're not going to do 3.2.3. You do not have your homework's due tomorrow, right? Yes, the programming assignment. I am going to give you this exercise to do, but people who watch the video will get the answer, and you're going to have the answer. So it's just basically you're going to put it in the Blackboard. So just work on it. So yeah, I'll put this up on Blackboard, and you can turn it.
We're doing 2.2.1.
We gotta do it for all of them. So
Okay.
So this one's pretty cool.
I'm just gonna.
This one first serve.
I was just thinking of, but you're right. Yeah. So the first one. We got 5.
So we got so first is 1, arrive at 0, and goes to 3.
So that's P1.
2 arrives at 2. But we can't have that, so we go from 3 to
9, right?
it's 3 to
Because if you
Six
start at
straight.
3,
9.
you can go 6, so it's 9.
They want like
It's gonna you need a lot longer this because it's keep going like long and long after this comes to
Yeah.
Okay.
If they want like the chart or do they want
let's get this at 9, 12, 17, you need 9.
So 0 to 1.
There's the 1.
And then that's
0
P1.
to
3, 9.
It should be 0 to 2 because 0, 1, and 2 is 3. So, it's 3.
Yeah, 1, 2, 3.
Okay.
Right?
Yeah. And 3 to 9,
1, 2, 3, 4, 5, 6.
and then 9 to 12, G12 to 17.
I was thinking for the 17, we gotta do like those.
3. 4 goes for